Is this not working? It's plugged in. Oh boy. It was one of these days. Tell me if anything changes. Feels like the thing is stripped here. Oh man. Let me pull out and try again. Well, the pins look good. There we go. That's how you hold your mouth. Yeah. Okay. The deciding factor. Okay, now we can go to, we are recording, so let's go to current slide. All right. Maybe we'll go to the current slide. Well, and Frank's here. He's the one who made the computer not work so he wouldn't miss anything. All right, okay. So we're just missing Cedric, Josh, and Ayana. Okay. Now, before we get going on that, let me go over a couple things. I may have mentioned this last time, but just in case I didn't, to make sure you understand. Normally on Fridays, I have office hours on the Birmingham West Campus from 8 to noon approximately, when we don't have meetings or other things. Okay. For the next 3 Fridays, in fact, counting last Friday, 4 Fridays in a row, that's not going to be strictly the case. Last Friday I was here on this campus because I had to make up a Math 112 class, and then I didn't have anything I had to go there for, so rather than wasting time driving, I just worked here. Okay. Well, this coming Friday, that's day after tomorrow, I have a dermatology appointment at 9:15, which is pretty inconvenient because if I do go to the Birmingham campus, I'm there before 8. I have to leave by 8:45 to get back to the Kirkland Clinic for my appointment and then go back to the Birmingham campus. So I'm going to check with my boss, hopefully sometime today or tomorrow, and see if he thinks it's necessary for me to come in, because I could sure do a lot more work from home than driving back and forth twice. So it's almost an hour wasted that I could actually get something productive done. But if there's something I need to be there for, I will. I will be there after my appointment's over. I can't imagine it's going to be much more than an hour, so I should be back on campus if it goes 9:15 to 10:15. Hopefully back on campus 10:45 to 11 o'clock. Only for an hour or so, but I will be there for the latter part. I'll probably stay past 12. All right, so that's this Friday. Next Friday, I'm going to Mobile. Okay, I've got a articulation meeting, the statewide articulation meeting. I'm on that committee, and I thought, surely I don't have to go to this thing. So I have to leave home about 7, drive 4 to 5 hours to get to Mobile, meet for 3 hours, and then drive 4 to 5 hours back. Okay, so 8 to 10 hours on the road for a 3-hour meeting. That makes a lot of sense to me, but I guess it does to everybody else too. So I won't be on campus at all that day. That's next Friday, week from this coming Friday. Then the following Friday after that, I have an eye appointment, but that's right across the road here at UAB West, and I thought it was going to be at the Eye Foundation Hospital in Southside, but they said, no, he's there that day. I said, good, that's right across the road from where I work, so I'll probably be on this campus that day, but if I need to go to Birmingham, I will. So, and then soon after that is spring break, and we'll need it. All right. I don't know of any other announcements, of course, except the North scholarships at Alabama A&M if anyone's interested in that program. Check your email. It's out there on your email. And there's a link there. You can find all the details and information. All right, any questions? Administrative questions or calculus questions? Is number 10 okay, or do you need some? You said something about number 10.
Oh.
Huh?
It was on my quiz.
Well, I understand that. I can't work a test question, but if you get one like, oh, you got it? Okay. Okay. If you, anytime if you find anything in the book similar, I'll be glad to work that if you're having trouble with a test question. Okay. So, no questions at all? Now, we're not quite ready for 3.2. We're still in 3.1, but I just needed more room to write. And that's probably the place with the most white space. So let's do example 3, page 170, chapter 3, applications, differentiation, 3.1, extrema on an interval. So here is f of x. Let me get my pen set up. There we go. The system is really slow today. Okay. Not recognizing things either. Okay. F of x, 2x, sounds okay so far, minus 3x to the 2/3. Maybe not as good. So find the extrema of that function on the interval -1 to 3. Now, you have to pay attention to the wording. When it says find the extrema, that means the extreme values, absolute or global maximum, absolute or global minimum. That's what they're looking for here. Not relative minimum or maximum. Not relative extrema, the absolute, the actual extrema. Okay? What does that? And then, too, the interval is a closed interval. Okay. So what does that mean? What are we looking for? What will we be investigating? Actually, 4 issues. You might group 2 of those together. How would you approach it? What would you do? Always a good choice is find the derivative. That's going to give you interior points that may be candidates for your local extrema. Okay? So f prime of x is equal to 2 minus, say again, my hearing's bad. 2, okay, 2x, I got that part, to the 1 minus 1/3. Okay. That's your, everybody agree with that? That's your first derivative. All right. You found the derivative, always a good thing to do in Cal 1 class, okay? But what do we do with it? What difference does it make? What do we need to know about that derivative? One of 2 things. Say again? Okay. Where it may be equal to 0. So let's set first this equal to 0. I'm going to need to rewrite that slightly, I think, because this is sort of hard to do calculus. Well, it's not hard, but it's different. So this is 2 minus 2 on the cube root of x, and set that equal to 0. What do we need to do with that? We need the x values that make that first derivative 0. How do we do that? Second? I can't hear. My hearing's so bad. Solve for x, exactly. How do we do that? Okay, you can do that, or, okay. Either subtract 2 or add 2 over root 3, over root, third root, cube root of x, if I could talk. Which way you want to do? Okay, so let's add 2 over cube root of x to both sides. Okay? And these go to 0. You have 2 is equal to 2 over the cube root of x. Now, I have a sort of surprised someone hasn't suggested this already, but we can do it anytime. What's next? Say again? Cube both sides is a good idea. So this will be, can I first, please, divide by 2? I don't like cubing 2 if I can help it. I'd rather cube 1. It's a lot easier. Okay. Not that 2's that bad. All right. So cube both sides. This is a 1 and that's a 1. Okay. Cube both sides, and that gives, we could do that now, and there's nothing wrong with it. We'll do it. That would be 1 is equal to 1 over x. Okay. Now what? Perfect. Okay. So this will be what? X is equal to 1. There is a possibility for a max or a min, an extreme value, where your first derivative is 0. Okay? And sure enough, if we put that in there, x equal 1, the cube root of 1 is 1, and 2 minus 2 is 0. Sure, that works. Okay? How are we going to tell whether it's an extreme value or not?
We need to find the y value.
Yes, which is the f of x, right? F of x is y. So we're going to plug it in back up in there. So let's do f of 1. That's what we found to be. And that will be what? Really tough. 2 minus, you got to take the cube root of 1 and then square it. 3. Okay, very good. All right, and what does that give you? Negative 1. So, could be that's a local minimum, could be a minimum value, could be a maximum value. But at least it's something to go with. And by the way, that's the only place where the first derivative is equal to 0, especially on that interval. But, and minus 1, positive 1 is in that interval. We had to check that. I forgot to. Okay? Are we done? Is that automatically our max and? Oh, no, probably not. What else do we have to do? Oh, okay, we got to do the endpoints. Okay? We can do that. So we'll plug those in. Alpha of minus 1, that's your one endpoint. What would that be? Negative 2 minus 3 times, again, what would that be? Negative 1 to the 2/3. Ugh. Okay. Okay. Is that going to be a 1 or a minus 1? Positive 1. Okay. Why? Well, the cube root of negative 1 is negative 1, but then when you square it, it becomes positive. Okay. So that is going to be a 1. And so you have, this becomes negative 5, right? All right. That threw out 1 being a local minimum, or a minimum. It could still be a maximum, and minus 5 could be a minimum. Could be. We still got 3, alpha of 3. And what would that be? 2. Oh, 6. Okay. 6 minus 3 times, huh? Pardon me?
Well, it's negative 3 times the cube root of 3 squared, which is
Okay. Now, I don't know that one off the top of my head. Okay, so if someone has a calculator, tell me approximately what value that is. 6 minus 3 times the cube root of 9. or you could have done the cube root of 3 and then squared it. It didn't matter which way you did it. It's going to come out the same.
6.24.
6.24? Okay. 6.24. That's a pretty... How did it wind up being positive? I mean, more than that. It's 6 minus that, right? I don't...
No, it'd be
Yeah.
0.24.
Okay. All right. Start back over. What is it?
So the cube root of 9 is 2.08.
All right.
And 3 times that is 6.24. So
Right.
6 minus 6.24 is
Negative 0.24. Is that what you said? Blah, blah, blah. Okay. Now, that is neither going to be a... No, that could be a max, couldn't it? Negative 1 still holds it for a min. 3 could be a max. 1 is out of the picture. Okay? Negative 1's in between those two values. Okay? Are we through? Have we found it? What are we missing? Go back to your first derivative. What are your critical values or critical points?
Where it doesn't exist.
Well, also where it doesn't exist. Not only where it's equal to 0, which we did, but where it doesn't exist. Is there any place that that derivative does not exist?
When x is 0.
Ah, it certainly does. It does not exist at x equals 0. So we got to do that one too. Alpha 0 is... Say again? 0. I was going to have trouble. I didn't need my calculator to do that one. Okay? Guess what that turns out being? That's your maximum. Okay? That's the only place where it doesn't exist. The only place where the derivative is 0 is 1. And then the two endpoints, everything's negative except 0 is 0. So that becomes your maximum value, and your minimum is at alpha negative 1. Okay? Let's see how the book did. Oh boy, the graph looks good. And yeah, so I guess conclude the minimum is alpha minus 1 is equal to negative 5, and the maximum alpha 0 is equal to 0. Yes. They do it in a little table, and if that helps you see it better, by all means do it. All right. Good deal. Any questions on that? Remember, not just where the first derivative is 0, also where it doesn't exist. We almost forgot that one. Okay. Now, example 4. This one is also, you can see larsoncalculus.com for an interactive version of this type of example. Find the extrema for this. Alpha of x is equal to 2 sine x minus cosine 2x. Okay, on the interval 0 to 2 pi, inclusive. What do we do first? Take a derivative, not a bad idea. F prime of x is equal to 2 cosine x. Excellent. Help me. A little louder. Okay. Permission granted. Did I hear a negative? Minus sine 2x. Yeah, 2x. Okay. Any help? Anything else? Please say yes.
The derivative of inside, so 2.
Okay.
2, and it's minus 2, minus.
Minus minus is plus. Very good. Everybody see that? Derivative of sine is cosine, so that was the easy side. This one is, number one, is the minus sign up front. Then derivative of cosine is minus sine, so that makes it a plus. Okay? And the sine of 2x, but then the inside derivative of that is 2. So that comes right. And what do we do with that derivative? Set it equal to 0. Always a clever idea, because that means a horizontal tangent line. Okay? And what do you do from here? All right. Glad we said that. Those are 1, so they disappear. But what now? Gag. We got cosine of x was the sine of 2x. How can we deal with that? Maybe start plotting points. Sounds like a good idea? Please say no. Okay. Or go back to trig class. Maybe a better idea. Anyone remember a double angle identity for sine? What's the sine of 2x? Uh-oh. Dredge them up. Now, if you can't remember these, they sometimes are located in clever places in the book, like the inside first sheet in your text. If you got a text, or if you have an e-text, it should be there somewhere. So there is a double angle formula for sine. Sine of 2u is now. I usually don't mess around with looking them up, or especially if I don't have a place or it's going to take me longer to look it up. Do you remember the sine of a sum formula? You remember that one? Sine of, say, a plus b. Do you remember what that one was? Sine a cosine b plus cosine a sine b. Always helps to plan ahead and not be walking down the page like this, but I did it anyway. Now, what if a is equal to b? Then this could become sine of 2a, wouldn't it? If a and b are equal, right? And that would be sine a cosine a, because they're equal, right? A, okay, plus cosine a sine a. Those are the same thing, aren't they? So that would be 2 times the sine a cosine a. That's what we got. So, all that to the side. Can I erase that, or does anyone need that longer? Huh? Yep. You want it? Okay. My writing stinks, but other than that, probably my feet don't smell too good either, but never mind. It's just one way to remember the double angle formula. If you remember the sum angle formula, then you can get double angle formula pretty quickly. So we verified that's right, right? Can I erase it now? Not that it really matters that much. I thought I had my eraser on. But it was so ugly calling down the side of the page there, I didn't want it that there anymore. Anyone take evidence? Okay. All right. Now, what do we do with the equation at hand, though? Ha! Sounds like a winner. Cosine x times 1 plus 2 sine x. And that's equal to 0. How does that make anything better? Yes, Zero product principle. If you got product of two entities that are equal to zero, one or the other, or both of them have to be zero. So either cosine x equals 0, or 1 plus 2 sine x is equal to 0. One or the other. Where is cosine 0 on this interval 0 to 2 pi? Pi halves. 3 halves pi. And that gets us past up to close enough to 2 pi. We can't go any further. Next. Okay, that's done. What about over here for the second equation? What would you do with that? Did I hear subtract 1? I couldn't hear.
Yeah, I was just saying subtract 1 and divide by 2.
Yes, yes. Subtract 1 from both sides. Wait, do it here. Okay, and divide by 2, so that'd be 2 sine x is equal to minus 1. Divide by 2, and you get sine x is equal to negative 1/2. Now we got to figure out where that's sine x is negative 1/2 on the interval 0 to 2 pi. First, where is sine negative? Third and fourth quadrant. So we're not even going to mess with the first and second. That's 0 to pi. Not even going to mess with that. So where between pi and 2 pi will that be negative 1/2? 5 pi 6, I think would be a good candidate. Okay, so x equal 5 pi 6. That's, whoa, that's not right. That's between 0 and pi. It's still plus 1 there. 7 pi 6. Okay, I think that one will work better. Okay, because that's past pi. Okay, any others? 11 pi 6. 1/6 pi short of 2 pi. Because the 2 pi is back at 0, so pi 6 before and pi 6 right after pi. That looks like a good choice there. All right, now we've got the 4 places where this derivative is 0. We have to consider also where the derivative is undefined. How about here? Here's our derivative. This thing right here. Where's that undefined? Defined everywhere. Sines and cosines are defined everywhere. So their sums, their products, their multiples, they're defined everywhere. Now, if one of those was a tangent or a secant or cotangent or cosecant, yeah, you may have problems. Sines and cosines, no. Okay? So we don't have to worry about that on this problem. What else do we have to consider? Endpoints. So how do you want to start this? We got 6 points we have to consider. 1, 2, 3, 4, 5, and 6. Which one you want to consider first? And how do we consider them?
0.
Okay, we'll start with 0. One of my favorites, okay? And what do we do with that? To what? Your function, alpha of 0. See what the value is. And what would that be? Sine of 0 is? Sine of 0 is? Oh boy, back to class. Back to trig, huh? It's 0. Sine of 0 is 0. How about cosine? Okay, first, what is 2 times 0? That's hard. 0. Cosine of 0 is 1, but you got a minus sign in front, so that's a minus 1. Could be a max, could be a min. We'll see. What you want to go to next? I don't care how you do this. Which one you want to consider next? 2 pi, okay? Alpha of 2 pi. I can almost guess this one, but let's try it anyway. What is sine of 2 pi? 0, so that's taken care of. What is 2 times 2 pi? 4 pi. Ooh, way out there. What is cosine of 4 pi? 1, and so you got a minus 1. We used to have a tie, folks, okay? at our endpoints. They're both minus 1. Okay? Next, pi halves. So we'll do f of pi halves. Whoa. What is the sign of pi halves? Okay? 2 times 1 is 2. What is cosine? Oh, wait, what is 2 times pi halves? One more time. 2 times pi halves. I have half a pi and I have another half pi. Don't give me a quarter pi. I want a full pi there, okay? Okay, I like my pi. Okay. So, that's pi. What's cosine of pi? Cosine of pi? Negative 1. Starts here, goes down there, okay? Negative 1, and but you got a minus there, so you got a 3. 2 plus 1 is 3. Now, am I doing this right? I'm just doing it in my head here. Correct me if you see any errors here. Next, 3 has pi. Alpha 3 has pi. Okay, what sine of 3 has pi? Negative 1. 2 times that would be negative 2. What is 2 times 3 has pi? Three pi, okay. And what's cosine of 3 pi? Ooh, okay. Okay, yes, negative 1, okay? And then you have a negative in front of that, so it's a plus 1, so you have a negative 2 plus 1 is another, it seems to like hanging around negative 1, doesn't it? Okay? Next. Oh, we've been waiting for this. You put it off till the last, didn't you? 7 pi over 6. Okay, what's the sign of 7 halves pi? Negative 1/2. Remember, that's how we got it, okay? Sine of 7, okay, and twice that would be negative 1. They're having negative 1 again, but it won't hang around too long. What's twice 7 pi 6? It's what? Okay, or you could shorten that to be, reduce that to be 7 pi thirds. That's good. Now 7 pi thirds. There's 1/3 pi, 2/3 pi, 3/3 pi, 4/3 pi, 5/3 pi, 6/3 pi, 7/3 pi. What's the cosine of 7/3 pi? Same as cosine of, it's 1/2. Perfect. Okay, but you got a minus in front of it. So you had a minus 1 minus a half. That would be minus 1.5. Are you happy with that? Okay, am I doing it right? It's a little abstract here, but okay. And the last one we've been waiting for. Okay, alpha. Well, we have either 11 pi 6. Okay, start with what is the sign of 11/6 pi? Negative 1/2. Remember, that's how we got it. Okay, and double that. Good old negative 1 again. Now, what's twice 11 halves pi? Yeah, 11 pi thirds. Oh, I don't have to go through that again, do I? Let's just do 6/3 pi gets us right back to the beginning, okay? And then, so you're 11/3 pi, you're just short of 12/3 pi, which you get you right back at the beginning again. So you're 1/3 pi short, so you're down here. And what's the cosine of that? Cosine of minus, that's 1/2, but you have a minus sign in front. So another negative 1.5. Boy, these things hang around in pairs, don't they? Okay, So what do we have? A clear winner for the max and a tie for the men, if I did it right. No guarantee here. Yep, they got it too. They put negative 3 halves, three halves, but that's the same as negative 1.5. So, yes, we have a tie for the men and a clear winner for the max. In fact, about the only place it goes positive, isn't it? Now, here is your picture of the graph for people who don't have books. Now, I can't hold it very long. There it is. There's your max up there at pi halves 3. You had an import here at -1, import there at -1, and then an intermediate point at 3 halves pi -1. And then these two, though, were down there at -3 halves. That's enough. You don't need to see anymore. Okay. Show and tell. Any questions? Now, I can't remember if I signed all the homework or not, but let me go on and do it again. Any of the odds 7 through 11, they're all at Calc Chat. 7's at Calc View. Either 13 or 15 or both, they're both at Calc Chat. Any of the odds 17 to 21, they're all at Calc Chat. 17's at Calc View. Any of the odds 23 to 39, they're all at Calc Chat. 25's at Calc View. Either 41 or 43 or both, they're both at Calc Chat. 41's at Calc View. Either 45 or 47, they're both at Calc Chat. 49's at Calc Chat. 51's at Calc Chat. 53's at Calc Chat. 55's is a writing one. If you see something there you might expand into a research paper, do so. Speaking of which, let me find the right class here. Uno, one person has done a research paper. We're almost at midterm, folks. And let me just get this word of announcement in here about midterm. Here at Lawson State, we usually, sometimes they forget, but they usually ask for midterm progress reports sometime after next Tuesday. Next Tuesday is the last day of the first mini-term. They'll ask for a midterm progress report. That's anybody who has a D or an F at midterm. Now, none of you are D or F students, but there are 2, neither of which are here today, that have not turned in the first test, or a paper, or the second test, okay? So I need something, I need a score in by next Tuesday, or else, or whenever they ask for it, or else I have to put in that you have an F. I'm preaching to the choir here because y'all are all in good shape, okay? Some shape better than others, but you're in okay shape. All right. Any questions? That was that. And if hopefully you know what your average was. If you need to boost it up a little bit, get either on your first test, get either your paper in or your second test in to try to help that. All right. Any questions on this one? Okay. I just sort of stopped in the middle of that, didn't I? I thought we were through. I see there's more problems on the next page. So the writing, that's what threw me off. Started talking about that. There's exploring concepts. 57 should be at Calc Chat, and 59 should be at Calc Chat. Then you can do any of the applied problems. 61 or 63, either of those two. Now, some of these have for further information, and if this is something of interest to you, I can't believe I'm reading this, the calculus of lawn sprinklers. I don't think I've seen that phrase before, but here it is. And they give you a possible reference, okay? And the other, design of honeycombs. I've seen that problem done before too. All right, then there's a couple true false, 65, 67. They should be at Calc Chat. Nice to think through. And there's a problem on functions that you might want to think through as well. Those upper level ones, you can decide whether you want to follow that or not. All right, any questions? 3.1. Okay, let's go back. Chapter 3, application of differentiation. 3.2 is Rolle's theorem and the mean value theorem. So we're going to deal with a couple of pretty important theorems in applying derivatives. Okay? So we'll understand and use Rolle's theorem, and we'll understand and use the mean value theorem. Two pretty good sounding objectives there. And we'll start with Rolle's theorem. And they start talking about extreme value theorem. Okay. Extreme value theorem states that a continuous function, this is one we did in the last section, on a closed interval, a to b, must have both a minimum and a maximum on that interval. If it's not on the in-between places, it's going to be at one of the endpoints. Both of those values, however, can occur at the endpoints. Now, because that's for an extreme value, it could happen at the endpoints. Okay. Rolle's theorem, named after French mathematician Michel Rolle, who you might find is a decent paper topic himself, gives the conditions that guarantee the existence of an extreme value on the interior of a closed interval. The conditions that guarantee that. And here's what his theorem says. If let f be a continuous on some closed interval a to b, same as before, differentiable on the open interval a to b. Okay? Don't have to be the endpoints. Now, if f of a is equal to f of b, are two endpoints. In that last problem, remember, it was. They were both at -1 there. Okay? If f of a is equal to f of b, then there's at least one number c in that interval a to b such that f prime of c is equal to 0. Okay? So if this function is doing anything, it needs to be continuous and it needs to be differentiable. Now, what does being differentiable bring to the table that just saying continuous would not bring to the table? What could you have with a continuous function that you can't have if it's a differentiable function? Say again? Cusp, exactly. Angles, corners, things like that. There's the first derivative does not exist, so that would be differentiable on the open interval. So continuous means you could have any kind of meetings of the two. Differentiable says that you got to be smooth. So this means smooth and continuous. Okay. So if you got a function that's smooth and continuous on the closed interval, smooth on the open interval, then, and if f of a is equal to f of b, if this thing is doing smooth and continuous things in here, someplace it's going to have a first derivative equals 0. Doesn't say max or min, it just says the first derivative is going to be 0 at at least one place on there. Now it says at least one. Can it be more than one? Sure. It can do all sorts of wiggling here. Or, this is sort of a weird thing, what if it's f of a is a constant, f of b is a constant, it's just a constant. Then every place there, the first derivative is 0. Okay. So there's going to be at least one. Okay. From Rolle's theorem, you can see that if a function f is continuous on AB, differentiable on the open interval AB, if f is equal, a is equal to f of b, there must be at least one x value between a and b, which the graph has a horizontal tangent. The first derivative is 0. Okay? Now, they show 1 being a relative maximum, which on this interval is an absolute maximum, not just relative, absolute. This wouldn't necessarily have an absolute minimum, not counting the endpoints. But you wouldn't have in this case, an absolute maximum. That's just one example. Okay? When the differentiability requirement is dropped from Rolle's theorem, f will still have a critical value on AB, but it may not yield a horizontal tangent. No, it doesn't. Okay? So therefore, Rolle's theorem wouldn't apply because this isn't differentiable. Okay? But it would still be a potential maximum. It would be a maximum. Okay? So here's example 1. find the two intercepts of f of x equal x squared minus 3x plus 2. What are the intercepts anyway? What intercept do you think they're talking about? Second, where the function's equal to 0. They're not talking about the y-intercepts here. Okay, they're talking about x-intercepts. Wish they had, oh, they did say it. I just didn't read it. Okay, two x-intercepts. Duh. Okay. All right. Find the two x-intercepts. That's where y is equal to 0, like you just said. This is not calculus, folks. Okay. And if y is 0, what else is y? From my pre-calculus algebra class, I used to tell them, I don't think, yeah, one of you were in it, I think. What is y always? F of x. So set this equals 0. Find the two x-intercepts. What are they? How do you get that? Hint. Hint. X minus 1 times x minus 2. Factor, right? And what does this give you? X equal 1 or x equal 2. Guess what? If those are x-intercepts, that means it's where they touch the x-axis. Guess what? That f is equal to this f, because they're both equal to 0, right? Now we've got a setup here that Rolle's theorem applies. Number one, this is a smooth continuous function because it's a polynomial function. Differentiable everywhere, continuous everywhere, okay? And we have 2 points that have the same value, 1 and 2. They're both 0 there. So that guarantees that there's at least one place in between 1 and 2 where f prime is 0, okay? So let's see, how do we determine that? Rolle's theorem tells us there is one. How do we find it? This is calculus. Take a derivative. You think that's the answer to everything, don't you? Okay. And what would that be? 2x minus 3. And then what you reckon we want to do with that? Set it equal to 0. And what does that give you? X equal 3 halves. Sure enough, that's in between 1 and 2. In fact, it's exactly in between 1 and 2. That's supposed to be a 2 halves. Somehow it came out a 3/3. 3 halves, it came out a 3/3. Something's wrong with the gray cells. Okay. All right. 3 halves. Exactly in between 1 and 2. They won't always be exactly in between, but that is it. Show that that exists. F prime is 0 at some point between those two intercepts. There, we've shown it. Okay. Actually, we knew it from Rolle's theorem, so we didn't have to show it, but we showed where it was. Okay. Oh, let's see how they did it. I was getting ready to go to the next one. Let's see how they did it. Note that f is differentiable on the entire real number line. And setting f equals 0 produces our two x-intercepts, x equal plus 1 or plus 2. Sorry. All right. From Rolle's theorem, you know that there exists at least one value c in the interval from 1 to 2 such that f prime of c is equal to 0. You know it, okay? To find such a c, differentiate f to obtain 2x minus 3. Set it equal to 0 because that's what it says. The first derivative equals 0, and that's going to be at 3 halves, just like you found. And there it is. Okay. And this we should have known was a parabola, which it is. And being a parabola, it's symmetric. And since you had two x-intercepts there, something in between was going to be, whether it was up here or down there. It's going to be down here because of positive leading coefficient. The x value for that would be exactly in between. Okay. Horizontal tangent exists there. Any questions? All right, they're skipping example 2. Let's not do that. So let's do it here. I forgot to bring the clock watch in again, so y'all let me know. Okay, this morning was crazy. F of x is equal to x fourth minus x squared. 2x squared, I believe it is, isn't it? Yeah. Find all the values of c on the interval open interval minus 2 to 2, such that, vertical line means such that f prime of c is equal to 0. Okay? Now, we're not using Rolle's theorem, we're going to illustrate Rolle's theorem. Okay? What do you reckon we're going to do? Dawson? Anybody? Take a derivative where f prime is going to be 0, so let's find f prime. And what would that be? Four x cubed minus 4x. Done. And what will we do with it? Set it equal to 0. And what one of the first things we might do? Divide by 4. I like doing that. Make the coefficients as simple as possible. Those of us become 1. 0 stays 0. Everything's hunky-dory. Now what? What's the F word? Oh, have I told you all that one? Huh? Factor. Okay. In this class, the F word is factor. Okay. What does that produce? If that offends anybody, I won't use it. Are y'all okay with it? Okay. All right. Okay. How will that factor? Or will it factor? Help me. Divide out an x, and what are you left with? X squared minus what? 1. Are you through factoring? Second? Second? Yeah, but are you through factoring?
I don't know, it'd be x minus 1.
X minus 1 times x plus 1. Okay, complete factoring, then set each equals 0. So here you have x equals 0. That's going to be in between there, and this one will produce x equal 1. That's going to be in the interval, and this will produce x equal negative 1. That will be in there too. We found 3 possible c's such that, and said find them all, and that's it, folks. That's all of them. Okay. 0, 1, and minus 1. All in that interval, open interval, minus 2 to 2. Now, some things that may help a little bit in thinking through this. What kind of function is this? I know you could answer all sorts of ways there. I don't mean polynomial, I don't mean fourth order. But even or odd. Second? Which? Anyone know? Even or odd? Or neither. It may be a neither. Even, odd, or neither. 3 options. What you guess? Even. Okay, it made it sound like a guess too. Okay, in a polynomial function, here's a real easy way to do it. Look at your exponents. 4 is even. 2 is even. Ha! And there aren't any odds, that would be an even function. If there was an odd in there, like plus x, neither. Okay, if they're off. Now this one happens to be, the first derivative is an odd function because all its exponents are odd. If one of those was saying, or if that was a plus 3 at the end, no, it's a neither. Okay. Now, what difference does that make? Not really a lot, except that you expect some symmetry here. It's symmetric. The function itself is symmetric about the y-axis, and the first derivative is symmetric about the origin. Not that it really matters, but you see it all sort of figures out that way. Okay. They didn't say graph it, but they are going to graph it anyway, and you'll see that. All right. We've done it. Okay. All right. They have at the bottom of page 175 a technological pitfall. We almost had one this morning, didn't we? Okay. Graphing utility can be used to indicate whether functions on the graph are relative maximum and relative min, but when using that, you should keep in mind that it can give misleading pictures of graphs. And here's the picture it shows. Here, looks like it just has a absolute maximum at x equal to 1, it looks like, and its value would be 1. Okay? But here's the function. F of x is equal to x minus, or 1 minus x minus 1 squared plus 1 over 1,000 times x minus 1 to the 1/7 power plus 1. One of my favorite functions of all time, by the way. The problem here is your viewing window. If you just use sort of a standard one, that's what it's going to look like. If you expanded the viewing window, you don't show it, you're going to find out there's a lot of other things going on here. Okay? So that's the problem of viewing window. Okay? You didn't have it wide enough. Okay. So now I think we're ready to move to the mean value theorem. Okay. There's some values that are really nice values and other values that are just plain mean. So you have to watch out for those. This theorem helps us out with those. Rolle's theorem can be used to prove another theorem, the mean value theorem. If f is a continuous function on the closed interval, we've seen that before, and differentiable on the open interval, we've seen that before, then there exists a number c on a to b, the open interval a to b, such that the first derivative of c is going to be exactly equal to the difference in f of a and f of b divided by the difference of a and b. What does that mean? What is this representing? Anybody? What is that? Slope of the secant line between your endpoints. Whatever your endpoints are, this is that. Now, if these are equal to each other, we're right back at Rolle's theorem. But if they're not equal to each other, this says there's some point c in there that when the slope between the endpoints, whatever it is a certain value, there's got to be some c in between whose first derivative at c is going to be exactly that value. All right? And again, keys here, f is continuous, f is differentiable. Okay. Wow, they don't do anything more, just popped it to you. They have a proof in the book, and it's really worth looking at. It's a pretty clever little proof. We just really don't have time for it. They have a picture of this really great-looking French guy. Italian, okay. Joseph Louis Lagrange. I would have thought that was a French name. By the way, 1736 to 1813, what was happening in that time frame? That was the extent of his lifetime. 1736 to 1813. French Revolution happened. Of course, he was Italian, or born in Italy. But that was happening in Europe. Of course, over across the pond, we had already had we're having our revolution as well. So this is a pretty unstable time in many ways. But he was held a position in the court of Frederick the Great in Berlin. Now, Frederick the Great especially with the Berlin in there, you think Germany. But if I'm not mistaken, this was probably part of what they called the Holy Roman Empire. I believe that was in existence at the time. So I'm guessing that's who Frederick the Great was. He was probably the Holy Roman Emperor, okay? And as my 12th grade English teacher used to say, and it was neither holy nor Roman nor an empire, but never mind, that was her little take on it. All right, so anyway, here's another paper topic. Mean value didn't get one, but Joseph Lagrange did. He did a whole bunch of things. You can check him out, maybe even write a paper on it if you're interested. Okay, so let's go to example 3. We're going to apply that theorem we didn't prove, but just came up with. Here's a function. F of x is 5 minus 4 divided by x. Find all the values of c on the open interval 1 to 4 such that F prime of c is equal to that thing, okay? That's basically the mean value. Before we begin, why didn't they have the interval from 0 to 4? Wouldn't that have been just as good? Anybody? Doesn't exist at 0. So you couldn't put an f of 0 in there. There is no f of 0, okay? So, no, couldn't do that one, okay? So, I'm glad they did 1 to 4. If they did minus 1 to 4, even worse. Even worse, because then you go across a discontinuity, which is, it wouldn't be continuous in there, and certainly wouldn't, first derivative would not be, it wouldn't be differentiable there. All right, so we'll use this. So what's the first thing we've got to do? Well, we've got to do several things. What's one thing we've got to do? Anybody? Oh, okay, I knew I could count on that. F prime of x is equal to what? Okay, before I do that, here's just a suggestion. You don't have to do this, but I sure find it better. I want to rewrite that function. 5 can stay 5. Minus 4 can stay 4. But I don't like over x's. I don't like x's in the denominator. So how could I write that? X to the minus 1. That I don't mind taking a derivative of. I don't like taking a derivative of the denominator, x in the denominator. You could use the quotient rule. As you can tell, I don't particularly a big fan of that. This is much easier. So what's your first derivative? Is what? 4x to the negative 2, which you could now write as 4 over x squared. Perfect. Okay? Now, you got to come up with a number between 1 and 4 such that this is the same as that, okay? Well, we need to figure out what that is. So let's do that. What is alpha 4? Okay, 1 minus 1. I mean 5 minus 1 equal 4. You're absolutely right. That's 4. What's alpha of 1? 1. Okay, so that's 1. So what is alpha 4 minus alpha of 1? 3 over 3, and that's going to be 1. So we need to find some place where f prime of x, we need to find the x where that derivative is equal to 1. The same thing as this slope is going to be that slope. How do we solve that? Say that one more time. I like that idea. Okay, so multiply this by x squared, multiply this by x squared. What does that give you? X squared is equal to 4. Where do we go from there? Say again? Square root of both sides, and what does that give us? Plus or minus 2. All right, so our answer is plus or minus 2. Is that right? Only positive 2, because we said all values C on the open interval 1 to 4. Minus 2 is not on that open interval, so we throw that one away and do plus 2, not the minus 2. And sure enough, we found a place where the first derivative is at, because plug in a 2 here. 2 squared is 4. 4 over 4 is 1. Sure, that's it. All right. Now, why did they call this finding a tangent line? For that, find all values in the open interval, blah, 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 blah. We didn't find the tangent line. We found the slope of a tangent line. That's fine. But we didn't find a tangent line. So why did they call that finding a tangent line? I don't know. But you can see largelycalculus.com for an interactive version, and they may take you a little bit further. It wouldn't be hard to find a tangent line, would it? And by the way, and that's why they're saying that, okay? And this was part of the proof of the theorem too. I'll show you on both of these. Here's a generic function f with f of a and f of b not being the same value. There's it. If that's a smooth continuous function in between there, whatever the smooth continuous function is at least one place that has that same slope. And that slope is going to be that's going to be the slope of the tangent line, because that's where your first derivative is equal to that value. So you're finding the slope of the tangent line. It wouldn't be hard to get the line itself. What would you do? A little involved, but not too bad. Okay? You know the slope is 1. Okay? We determined that. But if you plug in 1 up there, what do you get? We did it, didn't we? Yeah. F of 1 was 1. So, you have when you plug in 1. So 1, 1 is a point on the curve, and that's the point where the slope, you want the slope to be 1, point slope form. Figured out, you get the equation of the tangent line. To me, that's what finding a tangent line is. Not finding the slope of it, but finding the actual line. But they didn't ask for that. All right. Let's see how they work the problem, just to see if they carried it any further. Okay. The slope of the secant line between those 2 points is 1. We determined that. Okay. Note that the function satisfies the condition of the mean value theorem. What are those conditions? Must be continuous on the closed interval between 1 to 4. Okay? Wouldn't be continuous if it was minus 1 to 4. It would fail. You could not do the mean value theorem then. Okay? So, it's between 1 and 4, yes, it's continuous, and the first derivative exists. The only place it doesn't exist, well, the function doesn't exist at 0, and neither does the first derivative exist at 0. So that's out of the picture, but we didn't include 0 here. Okay. And the slope of the secant line is that conditions are met. Function is continuous and differentiable. That is, there it is. F is continuous on the closed interval, differentiable on the open interval. Okay. So there exists at least one number in C between 1 and 4, not counting 1 or 4, such that F prime of C is 1. Okay? Solving the equation, that's the same thing we got. We didn't quite write it that way, but we got it. The first derivative was 1 minus 4 over x raised is equal to, okay. And then it implies that x equal plus or minus 2. However, the same thing we implied, however, you're in the interval 1 to 4, so minus 2 is out of there, and sure enough, this is your place where the first derivative is the same as the slope here. That means it's a tangent line. Now, we didn't come up with that point though, okay? But they didn't want us to do the tangent line anyway. But it's at 2, 3. Okay. They didn't tell us to do that. But you can back up from that and find out at what value. Let's go back here. At 2, plug the 2 into the function, which is not on this page. So this one, plug 2 in here, and you get 5 minus 4 over 2. 5 minus 2 is 3. So the y value is 3. Now that you have the point and the slope, you can get the tangent line. But they didn't ask us to, even though the problem said that. All right. Oh, okay. They're skipping example 4. Do we have time? We do. Okay. So let's go back and do example 4. Two stationary patrol cars, this doesn't look like a good problem at all, is it? Equipped with radar are 5 miles apart on the highway as shown in the figure. Now, see, a few people don't have books. Can't hold it up for long, but I'll let you see what this is talking about. Now, that is a short-looking 5 miles, but you know, that's a long truck if that's 5 miles. But they're 2 patrol cars, 5 miles apart on the highway. So obviously theirs is not drawn to scale, okay? But we'll go on from there. 5 miles apart on the highway is shown in the figure. As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. Prove that the truck must have exceeded the speed limit of 55 miles per hour at some time during the 4 minutes. Okay. Everybody got a good clue on that? Let's write down the key here. So, patrol car here and here. I'll put them in the same direction. And this is 5 miles apart. Okay. At the first patrol car, it looks like he's going right to left, so we'll have first patrol car, he's clocked at 55 miles per hour. Okay. At 4 minutes later, he's here, so here's the time, 4 minutes. Okay, his V is 50 miles per hour. Okay. Okay. I have a big problem with this problem. Okay. They want you to use mean value theorem. You need to prove this. But to me, if he's going 5 miles in 4 minutes, his average speed is more than 60 miles an hour, right? Because that's a mile a minute. And he's going 5 miles in 4 minutes. So I rest my case. Done. You don't have to use mean value theorem or anything else. He's got to be going faster than that, okay? There's no way he could travel 5 miles in 4 minutes and not exceed 55 miles an hour, okay? Duh. So, I don't know. So, what they say here, they say let this be, t is equal to 0 at this point, and t is equal to 4 here. Okay, these are in minutes, by the way. Okay, no, it isn't. Okay, t is equal to, they get it in hours, 0 hours, and this would be 4 over 60 hours, which would be 1 over 15 hours. T, the second time, is 1 over 15. Okay. And they do it. His average velocity is then 75 miles per hour. So they do it. V bar is equal to 75 miles per hour. That's all you've got to do to show that, and that's all they're saying. Yeah. Mean value theorem says if the slope between these two is different, is greater than 55, then there's got to be some point in there where he's going at least 75 miles per hour. I would say there's points there he's not. Now, the 55 and 50 at the endpoints, that's just sort of not that important. I don't think. Well, I guess you had to have something there. But that still doesn't have anything to do with the problem because you're doing distance over time. So here, this is 0 time and 0 distance. This is time 1/15 of an hour at position 5. And when you do that, you get miles per hour. So the 55 at the beginning and 50 at the end is just sort of extraneous information that's not necessary for the problem. Okay? And so if indeed the average was greater than 55, there had to be some point in between greater than 55. Now, how are we doing on time? 15 minutes? Good. Okay. A useful alternative to the mean value theorem then is this. If f is continuous on A to B and differentiable on A to B open interval, then there exists a number c in A to B such that, this is a slight variation on it, that f of B is equal to f of A plus B minus A times f prime of C. Basically, all you did, remember your conclusion before, was there is some point f prime of C that's equal to f of B minus f of A over B minus A, right? Multiply both sides by B minus A, you get B minus A here, and then add f of A to this side, and there you have it. I mean, it's just rewriting it, okay? Rewriting mean value theorem in this form, okay? Keep in mind that polynomial functions, rational functions, and trigonometric functions are differentiable at all points in their domain, okay? With rational functions and some of the trig functions, you just have to be careful that you stay in the domain. You can't get where there's a vertical asymptote, which can occur for rational functions, can occur for trig functions, will never occur for a polynomial function, okay? So, just another way of writing that. Okay. Now, why did they tell us that? No special reason. And I'm almost wondering why they call it the mean value theorem. The only thing that's sort of meanish about it is the slopes are equal somewhere in between. It didn't say anything about the value being an average value, and that's what mean means. But anyway, that's it for this section, 3.2. So, homework exercises here, 3 or 5, they're both at Calc Chat. 7 or 9, they're both at Calc Chat. 9's at Calc View. Any of the odds 11 through 23, they're all at Calc Chat. 13's at Calc View. Any of the odds 25, either 25 or 27, they're both a calc chat. Do 29 is a calc chat, or should be. Do 31 is a calc chat and calc view. 33 is a calc chat, 33 and or 35, they're both a calc chat. 37 is a calc chat. Any of the odds 39 to 47, they're, all at calc chat. 47 is a calc view. Do either 49 or 51, they're both a calc chat. And do 53, it's a calc chat. There's exploring concepts. You can look at those, 55 and or 57. They should be at calc chat. 59, well, I'd say do any of the odds, 59 through, I'd say 59 or 61, do either of those two. They should be at calc chat. There's a think about it problem at 63. It should be at calc chat. You could do either 65 or 67. They're both at calc chat. 69 or 71. They're both at calc chat. There's a couple of true false, 73, 75. Think through those. Make sure you understand why they're true or false. And then you have a couple proofs, several proofs. Any of the odds 77 through 83 are proofs, and they should be at calc chat. And 85 is using the mean value theorem for another purpose. That should be at calc chat as well. All right, we've got time, don't we, to go to, how much time we got? 10 minutes? Oh, good, we got plenty of time. To 3.3. Y'all get the feeling the third test coming up quickly? Well, no, this is a long chapter, 3.9 sections, so we've got a while yet. But I need those first tests in. Of course, I'm preaching to the choir again. Y'all got them in. It's people not here who haven't gotten them in. So again, application of differentiation. Now we're at 3.3, increasing and decreasing functions and the first derivative test. Okay? Thought we already had the first derivative test. No, something else. All right. Determine intervals on which a function is increasing or decreasing. Okay, we've done that before, haven't we? Not in calculus, but that's not going to be too bad. We'll apply the first derivative test to find the relative extrema of a function. We've been doing that. Good deal. Thank you. What's that? Okay. Good deal. Okay, so let's look at increasing and decreasing functions. This seems like pre-calculus type stuff. And it sort of is, only now we're going to do it with calculus. You will learn how derivatives can be used to classify relative extrema as either relative minima or relative maxima. First, it's important to define increasing and decreasing functions. Now, this definition, just like it was back in pre-calculus algebra. Function f is increasing on an interval when, for any two numbers x1 and x2 on the interval, as long as x1 is less than x2, that implies that f of x1 is less than f of x2. Okay? That means the function is increasing for every x1 and x2 in that interval, any two numbers x1 and x2. And it's decreasing on an interval when, for any two numbers, x1 and x2, as long as x1 is less than x2, implies that f of x1 is, they got that backwards, didn't they? That should be a greater than. I hope they got it right in the book. No, they don't. And I had made a change in the book, too. They watched it. That should be a greater than sign. And in the book, I did it in red. I probably should here too, just to emphasize it's wrong, but I'll do it in dark. Okay, that's correct. I can't believe the book. And this is 11th edition, and this era made it through 11 editions. That's hard to believe. Okay, but they say the writers are human, so we'll let them get away with that. All right, the function is increasing when, as x moves to the right, the graph is moving upward. Decreasing when x moves to the right, the graph is going downward. So guess what that tells us? How do derivatives enter into play there? Well, here's a function. It's a rather weird-looking function. But we know, just looking at it, by our definition, for any value x1 and x2 on this interval here, the alpha of x2 is less than alpha of x1. Alpha of x1 is greater than alpha of x2. So that's a decreasing function there. Here it's constant. They did give us a explanation of the constant function, but then alpha, for any two x1 and x2, alpha of x1 is equal to alpha of x2 on that interval. That would be the case here. Increasing here for any two x1 and x2, x1 to the left of x2, then alpha of x1 is less than alpha of x2. That's increasing. Okay? Sure. Okay? Now, down here, they tell you the calculus way to say this. You don't have to check every 2 points and say, yeah, it's still decreasing, still decreasing. All you have to do is see what the sign, SIGN sign, of the first derivative is. If the first derivative is negative, that's a decreasing function. First derivative is 0, constant function. First derivative is positive, that's an increasing function. Isn't that much easier than checking every pair of points and say, yep, still decreasing, still decreasing. Yeah, that would be the easy way to go. Calculus is wonderful, isn't it? Of course, say yes. Okay. As shown in 3.5 below, a positive derivative implies the function is increasing, negative derivative implies the function is decreasing, zero derivative on an entire interval implies the function is constant on that interval. So here's your test for increasing, decreasing functions. If alpha be a function that is continuous on the closed interval a to b, we've seen that before, differentiable on the open interval a to b, open interval a to b, then if f prime is positive for all x's on that interval, f is increasing on that interval a to b. Okay? If f prime is negative for the entire interval a to b, the function is decreasing on a to b. And if f prime is 0 for every x in that a to b, then f is constant on that a to b. Okay? Nothing too new here, is there? Positive first derivative means function's going up. So here's example 1. Find the open intervals, they say S, okay, on which alpha of x, which is x cubed minus 3/2 x squared, increasing or decreasing. Okay? Oh boy, what are we going to have to do? Now here's something to keep in mind. This is a polynomial function. Polynomial functions are smooth and continuous. Okay? Smooth and continuous, meaning all the criteria are met for what the theorem that we've just been dealing with. He couldn't keep himself awake, did he? Okay. All right. Okay. So what might we do? Any ideas? Oh, good idea. Okay. You got a follower here, I think. Okay. F prime of x is equal to what? 3x squared minus 3x. Okay. Now, even though they haven't really said this very much here, we still are interested in, guess what, where that's equal to 0. So let's go on and set it to 0. Okay? And I'm jumping a little bit ahead here and making some assumptions I hope everybody can play with. What would we do next? Could divide out the 3, sounds like a great idea. Now what? Factor, and what does that give you? X times x minus 1. okay? That's equal to 0. Which means, what two values? X equals 0 or x equals 1. Two places where the first derivative is 0. Now, is it likely that this polynomial function that we started with is going to be constantly 0 anywhere? No, polynomials don't do that. To be 0 in between here but something else otherwise, you're going to have something not smooth. So these are just going to be passing values. So these are going to be critical values, either maxima or minima, okay? Now, they are going to do that later, but it seems like to me this is pretty obvious here that. Now, if it's a maximum, guess what? Increasing on one side, decreasing on the other. If it's a minimum, decreasing on one side, increasing on the other. It's got to be, okay? So we now have our function at least in 3 regions, okay? Anything to the left of 0, between 0 and 1, and anything to the right of 0, okay? And since there's no more places where the first derivative is going to be 0, and it's a smooth continuous function, it can't change direction anymore. So it's going to be strictly increasing or decreasing to the left, strictly increasing or decreasing in the middle, and strictly increasing or decreasing on the right of those intervals. Okay? So let's find what it's doing on each one of those. How would we determine that? Plug in what?
Plug into the function.
To what?
Plug in the values into the function.
Oh, okay. Okay, that's a great idea. So f of 0 is 0, okay? And f of 1 is, second, negative 1/2. Okay? Yeah. Okay, because this would be 1 minus 3/2 is negative 1/2. Okay. I've got an idea right now. If f of 0 is 0 and f of 1 is negative 1/2, it's got to be decreasing there, doesn't it? Because the derivative is 0 here, and the derivative is 0 there, whichever way it's going. But the thing is, it can't be 0 in between, so it's going to be strictly decreasing because it's positive here, negative there, it's going downhill. So I think we found an interval on which it's decreasing. Open interval, so this will be from 0 to 1. You always express your intervals in terms of the x values, the independent variable. All right. Are you okay with that? Does that make sense? Got to be, right? Now, there's no guarantee it's doing the opposite things outside of it. I can pretty much assure you it is, but no guarantee. So what might we choose? What we want to look at?
Can you just choose an x value that's lower than 0 and plug it into the
Absolutely.
derivative?
Pick test points. Something to the left of 0, and we could go on and put one between 0 and 1, though I don't think we need to, and then we can pick something to the right of 1. So anything to the left of 0 you might want to test?
Negative 1.
F prime. I'm interested in what the first derivative is, not what the function value. Though the function value would tell you something, but f prime at negative 1 would then be what? Remember, f prime was this thing right here. 3x squared minus 3x, okay? And that was, you said, that would be 3 plus 3, isn't it? No, wait. No, yeah, 3 plus 3, 6. So guess what? Looks like it's increasing, and that would be everywhere from negative infinity to 0. Right? Okay. Let's pick something. You want to pick something in between? We can if you're interested, but Okay? Then pick something to the right of 1. Keep it simple. F prime of 2. What would that be? That would be 3 times 4 is 12 minus 6. That's also 6, okay? Amazing, isn't it? Okay? So that means it's increasing out there. And since it's not 0 anywhere else, it can't change sign of the first derivative again. So it's increasing from there and also increasing from 1 to infinity. Decreasing from 0 to 1. And notice we put these intervals as open intervals. Don't ever block them in. It's not really easy to tell whether it's increasing or decreasing at 0 because that's where it's 0 or 1, you know. So just have the open intervals like that. Does that make sense? These two increasing, this one decreasing. All right, I'm sure they're going to do it slightly differently. How much time do we have? Huh? We're past. Well, guess what? No extra charge. Okay. I'm going to be generous today. Okay. All right. If you look in the book, let's see, increasing, decreasing, increasing. I think they got it right too. Good for them. Okay. Us next time. Remind me, we've already done it, but we'll look at their version of that next time. Now, let's see. Have you done enough on this for homework? I think you can do 3, and that should be at Calc Chat. And you can do any of the odds 5 through 9. They're all at Calc Chat, 5's at Calc View. I think you can do 11 through 17. They're all at Calc Chat, 13's at Calc View. And we'll stop there and pick up the rest of them later.
So whenever we're doing a product rule, do you want us to solve it out, or is that okay? Like we just have it set up?
You differentiate. Okay. Find what the derivative is. Yeah. What are you asking about?
If we
You
just
don't
set
set
up,
it equal to 0 or anything.
No.
You just find out what the first derivative is.
can we just? I was asking if we could just have the product rules,
Right.
and if that can just be the answer. Do you want us to solve it out?
I don't understand what you mean by solving it out. Simplify?
Yeah.
I like the thing simple. Okay. So, I mean, but that looks simple enough. I don't see any reason to do anything more. Yeah, that would be fine.
Okay.
Yeah.
I found one. An example. This one homework.
Okay, right. Let me. Well, I could do this on
The
here
test
too.
you use is different, yeah.
Yeah, okay.
Sine x plus 2 sine cosine 2y equals 4.
Okay.
So this is what I did. I said the sine x is equal, the derivative of this is cosine x plus, now this I'm going to do change. So I had minus 2 sine 2y, yeah, and then I had the derivative of this, which is 2y prime was 0.
Okay, good.
And then I said, okay, I got solve for this. I had minus 2 sine 2y prime equals negative cosine x divided by minus 2 sine 2y minus 2 sine 2y. And then, I should do it too.
Yeah, well, you can do it now.
2y prime equals this. I always have to erase this. That's 2 sine 2y. I can divide out too.
Yeah. Divide with it.
All this divided by 2.
Yeah, but just make that 4.
Oh, okay.
Yeah.
Yeah. That's
Okay.
really what I
And then minus is plus. Yeah.
equals, cosine x over 4 sine, don't do none of that too.
2y.
2y. I was working it right.
Yeah, okay.
And leave it like that.
Yeah, that's what I was looking for, okay. Okay, and, okay, which one was this?
That was
You got this?
this was
Was it a homework? Okay. let's just check that. 15, which section do you remember?
Implicit differentiation.
That's 2.5, I think it was. So let's do 2.5.
Click on it in my book. I don't even think about that. On my computer.
See, I'm so old school, I think of this, okay? Because it's the only way we used to have to check things. What number was it?
15.
15. One more page. Cosine x over 4 sine 2y. Look at that.
I know how to do it. Okay.
All right, good deal.
This was not sure.
Okay. Man, I was recording.